Welcome! This video introduces the idea of parallel and serial processing and non-determinism in BYOB. So I've got a BYOB program loaded, serial versus parallel. If you want, you can load it up yourself and play along. So in this program, there are three sprites. This little yellow guy on the right-hand side called serial, and on the left-hand side we have these 1 and 2, the two parallel sprites. Their missions are to basically fill the screen with copies themselves. And so the stamp command just leaves a print that looks like a copy of the sprite that does the stamp. Each of the three sprites has basically the same program. When they receive go, they're going to repeat for a bunch of y's and then for a bunch of x's, go to that location and leave a stamp. You don't have to worry too much about how the loops are working, just that's going to cause them to try and cover the screen with copies themselves. And everything gets going when I hit the flag button. We're going to clear the screen, broadcast go. Each sprite will get the go command and start working. So here we go. All right. First thing we notice is that they're all working at the same time. And second thing that's pretty obvious is the left-hand side is going to get filled up faster than the right-hand side. Right? On the left-hand side we have two sprites, two programs working to do the job. On the right-hand side we just have one. This is the fundamental idea of parallel processing. If we can have two programs or two threads working on the same job at the same time, we hopefully can get it done in half the time. Now, behind the scenes, BYOB really can't run all three sprites at the same time, so what it does is something called time slicing. Alright, so we've got the three sprites, and what happens is first BYOB gives one of them a little slice of time to do some work. And so what we might end up with is serial gets a chance and it draws one square, and then parallel 1 gets a chance and it draws a square, and then parallel 2 gets a chance and it takes its turn, and then we go back to serial and give it a slice of time to do a piece of work, and then parallel 1, and then parallel 2. So in this way, by giving everyone a little slice of time to do their job, we make it look like, as long as we do this fast enough, it makes it look like the programs are running at the same time. And that's basically what's happening in BYOB. And if you have a real old computer that's got what's called a single core processor that can only do one thing at a time, this is how they run multiple programs at the same time. How you can have an antivirus program running at the same time that you're, say, watching this video. So let's go back to BYOB now and explore a different program. So here we have the determinism program loaded. We've got four sprites, blue, gold, cardinal, and white. And they're all waiting for the go command. And when they get the go command, they're going to do fill screen. And then after they're done filling the screen, they're going to set finish, this variable, to whatever was already in finish plus their own word. So basically they're going to add their name, blue, gold, cardinal, or white, to the finish list when they're done. And just like last time, everything's going to start when we issue the go command. We're going to clear out the finish and broadcast go. So what's the fill screen command? Well, it looks a lot like those the ones we have from the parallel versus serial. We're just going to kind of repeat for y and for x, go to location, stamp, and then hide themselves at the end so that all we see is the stamps that are left over behind. Now, all the sprites are going to start down the lower left-hand corner and work their way to the upper right. So I'm going to hit the flag and we'll watch what happens. So they blast through, and I can see that the first to finish was white, and then cardinal, then gold, then blue. And because blue was the last one through, that's why all we see is the blue. So I'm going to clear things out and run this again. And this time carefully watch as they're covering the screen. So you see flashes of color at the start. A little flash maybe of red, maybe even of white, definitely of the gold. And then blue comes through and wipes everyone clean. So basically what we have happening is that same situation of time slicing where white goes in and gets a chance to draw itself, and kind of this is the order it's happening. White draws itself, and then almost immediately cardinal, the red, wipes that out and replaces it with red, draws red over the top, and then gold goes and draws itself, and then blue comes and covers everyone else up. And it's always happening in the same order: white, cardinal, gold, blue. White, cardinal, gold, blue. The time slicing that BYOB does is deterministic. It's always going to pick kind of the same sprite based on their position on the screen to go first, and then it's always going to give everyone an equal slice of time, and so we get this predictable result. Now, if we have a real program running on a real processor competing with other real programs, we don't get this nice deterministic behavior. What we get is what's called non-deterministic behavior, where we can't predict exactly what's going to happen. Right? Sometimes one program takes a little longer than usual to run, or maybe it has to wait for some information to come through from the hard drive. And so a job that we expect to see happen one way may not always play out that way. We expect to see white, cardinal, gold, blue. Well, if there's some pauses in there, that can throw off the ordering. So in BYOB, to get realistic non-deterministic behavior, what we have to do is introduce some timing issues. So I'm going to edit the fill screen. And basically what I'm going to do first is make everyone pause a little bit before they get going. All right, so let's go ahead and use a wait. And if I wait 1 second, that's not really going to do anything too interesting. So instead, I want everyone to wait between 1/10 and a full second. So I'm going to pick a random number from 1 to 10. I'm going to divide that by 10. So every time this block runs, there's 0.9, 0.1, 0.2. We're always going to get some fraction of a second. So everyone, when they do fill screen, they're going to wait a random amount of time and then start going. All right, so I'm going to clear things out and start this up. All right, this time, white must have waited the longest because it came through last. And we can see the order was cardinal, blue, gold, and white. If I run this again, I'm probably going to end up with a different order. This time, cardinal, the red color, was the last one, and so that's the one we see. This is typical non-deterministic behavior. We can't predict exactly which job is going to run first and get going first. What's still atypical about this is that once we get going, they all are running at exactly the same speed. So the fact that red started up last means red was last all the way through. Now, in a truly non-deterministic system, each time we go to stamp, it might take a different amount of time. So what we might expect to see is something more like this. We've got the 4 blocks, and maybe light blue goes first. And after blue gets its turn, maybe red gets a turn, and then white gets a turn. And then maybe the next unit of work that happens is blue again, and then white. And then finally gold is ready to do something, and it gets a slice of time, and it can do something. But this is classical non-deterministic behavior, where from second to second, we don't know exactly who's going to get what done. We can't predict the order at which the screen is going to get filled up by who. So to bounce back to BYOB and look at this there, I'm going to modify fill screen again. All right. So I'm going to take that same wait block, only instead of having each of the sprites wait once before it starts trying to do stamps, I'm going to introduce this wait right into the middle. So changing the location of the wait is a pretty big deal, because now every time one of these blocks goes to a new location, is ready to stamp, first it's going to wait a little bit. All right, so it's going to kind of keep waiting before each stamp and a random amount of time. If we start this up, it's going to take a lot longer because the characters are waiting more often. But more importantly, we're going to see some weird results. So you can see that someone's out in front. Currently it looks like yellow is kind of out in front. And and other people are lagging behind. In this case, white looks like it's pretty far behind, but red was actually the first one to be going slow. And so for a period of time, we may have one color showing, and then it's covered up by another. And in this case, white is lagging so far behind that it covered most of the screen, except for that very first square. If I clear things out and run it again, well, we're going to have kind of a different order. Red is the chaser this time, and it's the one that's way behind everyone else. And I can see it's pretty far behind blue, so it's probably not going to catch up. But it's entirely possible, if I try this enough times, that the last place person's actually going to change over time. So if the blue one ever kind of overtakes the red one in this scenario, we could very easily end up with a scenario where the blue is covering up most of the screen, and now red is the chaser. And so we don't even end up with one solid color covering the screen. We end up with this situation where part of it's blue, part of it's red, and then blue was trailing again, and then red was the last one through. So this really kind of messed up view where it's not that any one color won, everyone got in to do different parts at different times.